So let's first take questions specifically about the homeworks, problem sets, ideas, concepts, anything to do with the Chomsky hierarchy, which is everything. Problems you had trouble with on the last homework or any of the homeworks. Problems that you just want to get hints on or answers to. I'm in a generous mood, so ask me anything. Everything is crystal clear? Yep.
Is there a way to do two-set without doing like the graph translation on it?
Yeah, I mean the graph translation is basically a depiction of what's happening in two-set, chasing the implications around. But you can do it without specifically, explicitly constructing a graph, right? Just by going over the clauses and, you know. But a graph depiction is as good as anything. Yes. You had a question?
Yeah, I still don't understand how to do the two input gates. Like most of the Boolean function requires exponentially number of two input gates.
Yeah, so most Boolean functions require exponential number of gates. And the fact that the 2 input is irrelevant. It could be 3 input, same result. 5 input, same result. And it don't have to be ands and ors, and it could be any one of the 16 different 2 input Boolean functions, same result again. So how would you answer? Let's turn it back to the crowd. Anybody succeeded in proving that the number of that most Boolean functions require an exponential description of any kind? Never mind using gates, but even in English, they will require an exponential description. Even if you do a song and dance about how they work, literally, say they work this way and they work, you'll be doing an exponential song and dance. Yeah. All right. So he's right, but let's answer it without using the word random and entropy, because those are tricky things. How many here know the definition of entropy? Okay, but it's hard to wrap your mind around it in an intuitive way. Is what I'm getting at. So you're right. You could do it this way, but let's argue it using say pigeonhole principle. Something much more discrete, concrete, straightforward. Let's not go to statistical lengths to prove it. You don't have to, is what I'm getting at.
So,
yeah.
For homework 1, we had that question: how many Boolean functions can be? If you have inputs, how many different Boolean functions can be written or something? I think the answer was 2 to the 2 to the n.
Yeah, so he's saying there's 2 to the 2 to the n different Boolean functions. Go on, and what can you conclude from that?
And then I think we need to calculate how many number of circuits you can build with gates. So you only can build this much circuits, but you have this many functions. That means I'm lost.
Okay, fair enough. But it's still a very good direction, is to ask yourself how many different objects are there that you're talking about, and the answer is 2 to the 2 to the n, right? So then what can you conclude from that about this lengths of descriptions?
More than half of those functions require an exponential number of gates. Is that what you're trying to prove?
Yeah, or any kind of description. Never mind gates. Describing a Boolean function using gates is one type of description. Describing using a truth table, like you said earlier, is another kind of description. Describing them simply by using words, like you describe an AND function by saying, if any one of the input bits, is a 0, then the answer is a 0. If they're all 1, the answer is 1. That's an English description. And it's just as good as a truth table, because you can convert that to a truth table and vice versa. Or you can convert that to Boolean gates. But let's just use a counting argument, pigeonhole principle. You have 2 to the 2 to the n objects. You can number them 1 through 2 to the 2 to the n, right, for example. And then you could say function number 17, and you'll know which one I'm talking about. If I say function number 50, or function number Google, and you'll know which one I'm talking about if you dovetail and enumerate all the functions one at a time. How many say you can do that? You can just dovetail, you can just number them. How high of a number are you going to have to go to if you assign each one a unique integer? And by the way, each one has to have a unique integer. Otherwise, if one integer stood for 2 different Boolean functions, they ain't going to be unique. So it's not a proper description because it's ambiguous. So each function better get a unique integer. So let's say we use contiguous integers so we don't waste integers. Natural numbers 1 through 2 to the n. So we need 2 to the 2 to the n different integers to represent Boolean functions. On the high end, 2 to the 2 to the n, how many bits are needed to represent numbers around that quantity, that range, 2 to the 2 to the n? 2 to the n. 2 to the n bits to just represent that integer. And it puts a lower bound on any description, never mind just an integer description. Right? So the size of most of these descriptions will be 2 to the 2 to the n. Remember the lily pond we said earlier, exponential growth. If something goes from 1 to powers of 2, that last power of 2 accounts for half of all the objects. How many get that? Right? So 1, 2, 4, 8, 16, 32. 32 is all the previous powers of 2 added together. So every power of 2 that's new, that's larger, is most of the total that you have. It's half plus 1, or the total plus 1. That's most right there. That's the word most in this question. It's that last half. And that last half all require 2 to the 2 to require 2 to the 2 to the n in magnitude and 2 to the n bits to represent those things. And in terms of Boolean gates, it's not going to be any less than that. The description, the minimum description is 2 to the n, and if you try to use gates or truth tables or anything else other than just an integer, it'll be at least that large, because there's 2 to the 2 to the n of them. Okay. So there's just too many functions to represent them all succinctly. So some of them will have very long description, no matter what the description is. English words, hand waving, truth table, Boolean formula, whatever it is. By the pigeonhole principle, if all the descriptions were shorter than 2 to the n, there ain't going to be enough of them to represent that many functions uniquely. There'll be clashes, and you'll have ambiguity. It's a pigeonhole principle. It's a counting argument. So just take the last half of them. In other words, the largest half of these integers. Never mind all the smaller ones. So yeah, the small ones that don't take many bits to represent. But at least half of them will have a description that's exponential. That's what we're saying. We're not saying which ones. We're just saying, again, by counting arguments, at least half will be very large. And just like we're saying, at least half of random strings, I'm going to go back to randomness since you mentioned, at least half of random strings are incompressible. Why? Take strings of length n, and if they're all compressible to size n minus 1, there's only half as many compressions as there are strings. F of many compressions of size n minus 1 as there are strings of size n, because n is bigger. 2 to the n is twice as big as 2 to the n minus 1. So if all the strings of size n were compressible to size n minus 1, there'll be, it'll be non-unique situation of compressibility and uncompressibility. And so most strings of size n are uncompressible. By most, I mean at least half. And the same with the Boolean function. So I know it sounds kind of bizarre that there's Boolean functions that cannot be expressed in less than exponential size description at the very minimum, no matter what your description is. Boolean gates, truth table, English words, hand waving, equation, whatever it is. But it's true because there's just so many of them. And some of them are very, very complicated. You know, some, again, back to entropy that I mentioned earlier, some are very high entropy in the sense that the function that they compute is so esoteric, weird, unpredictable, hard, strange, complex, that there's no shorter way to express it than exponential size description, whether it's Boolean gates or anything else. So that's sort of the point of this question. There's just too many functions, not enough description, not enough short descriptions. So many descriptions will just be long, very long, exponential size, in fact. That's all. Does that make sense? Is any other questions about that? So this thing about Boolean gates of 2 inputs is a bit of a red herring. I could have said 3 inputs. I could have said, you know, other kind of gates, not just, you know, whatever. You know, could have said, you know, not Boolean logic gates, but, you know, base 3 logic gates where there's 3 values, 0, 1, and 2, or something, or whatever, as long as the output is 0, 1, or whatever. So you know, the size of the atoms, the atomic units that you're using in your description, whether they're Boolean gates or other things, is irrelevant. As long as they're constant, you know, you'll need an exponential number of them, basically, to represent the whole thing. Okay, any other questions or hurdles or concepts or homework problems or whatever? What else was a stumbling block in the homework? It's not just the last homework, but, you know, any homework. How about anything on the problem sets? All 7, you know, however many, you know, 6 or 7 problem sets. 7, I guess it is. 7 problem sets, hundreds and hundreds of questions. Everything is perfectly clear. No questions about anything. That would be surprising. Yeah.
Closure properties of like P and NP.
Yeah. So which ones in particular? So clean closure of P and NP. So P and NP are closed under clean closure. Mm-hmm. Yeah. And so you can guess, you know, the unfactoring of a string into pieces, and then, you know, verify each one, you know, separately, or run each one through the algorithm separately, and yeah, so they're closed under clean closure. They're closed under concatenation as well. You know, P is closed under complementation. NP, we don't know. That's the NP co-NP question. Yeah, so when it comes to non-determinism, negation is usually problematic, right? Because a negation of there exists is not another there exists. It's a for all. And for all is not the definition of a non-deterministic acceptance, you know, computation. It's so that's, you know, that would be, you know, complementation is a problematic closure property whenever you have non-determinism involved. It's not always, like for space, non-deterministic complementation of non-determinism could end you in the same space. That could happen. But for time, it's problematic. Okay, any other concepts, questions, problems? Let me ask you a question. You know, just throw it out there, see what happens. Is there an algorithm that spits out a bunch of C programs, each one always halting within polynomial time for some polynomial, I don't care which, The program could depend on the program. So one program could be in quadratic time, one program could be in cubic time, one program could run in linear time, but always within that time asymptotically. Can you have a C program that prints out a list of programs, each one running in polynomial time, such that for every problem in P, one of those programs solves that problem. At least one, could be more, solves that. In other words, can you enumerate a set of programs that between all of them represent every single language in P in terms of what these programs do and don't do? And if so, what is your algorithm? How would you write such a piece of code that spits out an infinite set of other programs that together cover all of P and nothing but P? How many understand the question? Okay, any questions about the question, what I'm asking you to do? Yeah.
Is that equivalent to say that the language of P is decided?
No, it's not. It's not equivalent to that. So I'm not asking you for a particular program whether it runs in polynomial time or not. That's undecidable, actually.
I'm trying to convert it to deciding a membership.
Yeah, I know, but it's not the same.
Okay.
So I mean, it's a good try, and it's something you should try. But the problem of I give you a program, you tell me whether it runs in polynomial time for every input, that's undecidable.
Since P is countably infinite, we can just put every string. We can write every problem in P in binary, for example, and write a program for that particular problem.
Yes, but how can you ensure that you're hitting all the problems in P and not problems that are not in P? In other words, so some of the strings that correspond to programs that you're spitting out may not correspond to polynomially time-bounded programs. Some of these programs may run forever or even take exponential time or something else.
I mean, you can start by writing down the problems in P.
How would you do that? How would you write down all the problems in P? That's part of the issue here. Okay? What's an algorithm to just write down all the problems in P? Because that'll have to be part of your algorithm. And you cannot write problems that are not in P, and you must write all the problems that are in P. So there's two different tasks here. It's the whole truth and nothing but the truth. So you got to get all of P and nothing but P here. Yeah.
We know that the busy beaver function is nothing but the largest. Let's talk with respect to time because it's
Mm-hmm.
largest time, and then the program would halt. So if we could compute the busy beaver function for polynomial time, which would be a polynomial function with respect to the input, then we know that after that the machine would halt.
Okay, so you're saying if we can compute the beaver function, then maybe you can use it as a subroutine. But we can't do that because it's undecidable and it's not computable, right?
But we did bring down the halting problem for P to the SAT. So is it possible for us to bring down to the level of P?
You mean like the busy beaver problem for P or something like that?
Yeah.
It's an interesting idea, but then you'd have to explain how, if you're saying that you'd have to explain how that would work. Because I'm asking for a piece of code. Right? Any other thoughts?
I think in general, checking the runtime of a program is undecidable.
It's undecidable. Yeah. And not just checking the runtime, just determining whether the runtime is infinite or not. That's it. That's undecidable right off the bat. Never mind exactly what the time is.
If you guarantee, if someone gave you the guarantee that this program will halt, but I'm not going to tell you how long it will take with respect to the input.
That's right. That's right. And even if I tell you it halts, it's undecidable to determine whether it halts in polynomial time or not. specifically. So it's hard, that's hard to tell. It's impossible to tell algorithmically. Yeah.
If we can print down the problems in P, then we can determine if SAT is in P or not. For example, we can print down the problems of any event,
Mm-hmm.
lexicographic order. Then at some point there is a SAT instance. Then we have to decide if it's in P or not. Then our program should solve this problem that SAT if SAT is in P.
So you're arguing that it cannot be done, because you're saying if you could, then P will be equal to NP or something, something like that, or.
If we could, then we could solve the P both ways.
Okay. And by the way, what do you mean by writing down problem? What do you mean by writing down a problem in P? What would it look like? That in quotes.
Every string in lexicographic order, and then we can determine this string is an instance of a problem, a collision of a problem. We should decide if it's in P or not.
Okay, and you have to be careful. So are those strings instances of SAT or colorability or both mixed together, or?
Any problem that we have to decide if it's, our program has to decide if it's in P or not. I mean, if we could write that program, we have to write.
Okay. So let's make sure we don't make type errors. So a problem is an infinite set of instances. For example, satisfiability is an infinite set of propositional formulas that are all satisfiable. Three colorability is an infinite set of graphs, all of which are three colorable. So we say writing down a problem in P, are you going to, is that description the set of all satisfiable formulas, infinite set? How would you write an infinite set as a string? Strings are only finite, right? Every instance is a finite. So you have to be a little careful here. Any other thoughts? Or you had a thought? Yeah.
So we're kind of thinking that like an analogous problem might just be to enumerate Turing machines that only recognize decidable or only accept the decidable language, and then you're getting a halting problem situation because decidable Turing machines are always halting and recognizable are sometimes halting.
Recognizable can always halt as well, right? It has the option, but not the obligation to run forever. It's optional. The running forever is optional. And look at this, right? The recognizable is a superset of the decidable. So everything that's decidable is also recognizable. It's contained here. Recognizable doesn't mean you have to run forever on anything. You could always halt and still be recognizable. You have the option to run forever, but not the obligation to do that. It's optional. But it's another good try. What else? What do you say?
Showing you have a decidable set of languages even is undecidable?
I can see why you're trying to do that, but that will lead to the result that it's not possible to write a program that prints out. So let me just say it is possible. So I'm giving you now a big hint. I'm telling you what the answer is without the proof yet. So it is possible to write a piece of code right now. You can write it this evening that'll spit out an infinite sequence of programs. Each program would correspond to a problem in P. Each program will run in polynomial time. And every problem in P will have a program on this list that solves it. Put another way, every language in P will have a program on this list that accepts it, that decides it.
And this program does not produce anything else, just a solution for the language.
Each program solves a problem in P. Right. So for example, one program sorts. Another program does binary searches. Another program multiplies two matrices together. Another program runs Dijkstra's algorithm. Another program runs Prim's minimum spanning trees, and so on and so on. And every problem that's doable in polynomial time will correspond to at least one of those programs that your code will spit out. So your code will spit out an infinite, your code will never halt because it spits out an infinite number of other programs. And all of P will be represented among them. And nothing but P will be represented among them. The flip side is important. Why? Because if you just wanted to print out a set of all programs, you could easily do that. Take all strings and sigma star, run each through a compiler. If the compiler compiles it correctly, that's a valid program, and spit it out. But who knows what it does? It It may not solve the problem in P. It may not even always halt. It may solve the problem in P, but it will take exponential time to do it as opposed to polynomial time to do it. I can easily sort in exponential time. Let me show you how. Take the input, create all permutations of the input, print out the monotonic one. I just sorted, but I sorted in factorial time. So just because a problem is solvable in polynomial time doesn't mean that every algorithm to solve it runs in polynomial time. You can take arbitrary amounts of time to solve it too. That's not hard to do. But on my list, every program on my list will run in polynomial time necessarily. Yeah.
Well, I mean, I don't know if this is as comprehensive as you want. You can just check the conditions in like your loops.
What's that?
So, you check the conditions on your loops.
Okay.
If the so depending on what those conditions are, like for example, if I have a while loop, I might not, that might not let my program halt depending on whether, depending on what my input is, depending on what, and it's asking, so if you can sort of check that, your conditions, will let you halt, and then you can sort of count through.
Yeah, so you're suggesting some sort of a analysis of loops and iterations and try to see if it's polynomial or exponential kind of bound. You're trying to kind of solve the halting problem in disguise there, right?
Yeah, I mean, I think it's, I don't think that this approach would certainly work for everything, but I think it might help with regards to the if it's in P or not, because well, never mind.
Okay. No, I mean, it's an interesting idea. Try to do an analysis of loops and how long they take to run and so on to try to see if it's polynomial time bounded or not. But let's just say it's undecidable whether a program runs in polynomial time. If I give you a program and ask you, is it running polynomial time or not? It's undecidable, which means any such analysis ain't going to happen at the end in general. Now, in some cases, it might work. If all the loops run in fixed hardwired constant times, one loop runs 50 times embedded within a loop that runs 100 times embedded within a larger loop that runs 1 billion times, well, it'll run in time 100 times 50 times 1 billion, and there's no two ways about that. But the loop variables could be variables, and those could depend on other things and in a very complicated way. And in general, it's impossible to do such an analysis. Yeah.
Yeah, I was just gonna say, like, there are like, if you think of like a program that takes in plugins that execute code, and like those plugins are generated randomly, and you can show that sometimes the plugins all run in polynomial time, but sometimes they can't. Then you end up in a situation where only at runtime you know the runtime of the plugin.
Okay, so first observation is, you must be glad I didn't put this on the final exam. Let me tell you the answer then, or an answer. There's probably many ways to do it. So start. Yeah. What do you say?
So, like Rex theorem, only trivial properties are decidable, and the answer to this question is on the language in P.
Okay, so Cook. It's hard to apply Cook's theorem here because Rice's theorem, because Rice's theorem applies to properties. Here, we have programs, not properties. So Rice's theorem applies to properties of languages.
Right.
Here we have computer codes. You can't apply Rice's theorem to codes or to programs or to Turing machines. You can apply it to languages, which are properties. Properties are sets of languages, right? So you have to be careful about types here.
But isn't that all the programs we're talking about here corresponds to, like, you could encode them in a way that it corresponds to the language?
You could, but the set that you're applying Rice's theorem to is a set of languages.
We can, but can't we consider that the solution to that problem be a set of languages?
Yeah, exactly.
And then say that those languages can't exist because of Rice's theorem?
those languages all exist. They don't not exist.
The languages
Their membership
in that set is not decided.
Yeah, well, that may be true, but I'm not after languages here. I'm after a piece of code, a single piece of code, a program that has this behavior that I described. So rhizosome doesn't apply directly to that piece of code and shows that it doesn't exist. You have to, you're making a subtle type error here. You're applying rhizosome to animals and minerals and vegetables, not to properties here. And I'm being, deliberately dramatic by switching the types. It's not the same thing, yeah.
Are there a countable or uncountable number of inputs for the program?
You tell me. A program, how many inputs does it have? Countable or uncountable? How many say countable? How many say uncountable? It's countable by majority vote. But seriously, why is it countable? Seriously.
You can arrange them by length.
Yes, each input is a finite input, so there's only a countable number of.
Can you dovetail through all possible programs, all possible inputs for a finite amount of time on each of them?
So dovetailing is a good idea here, but we're not going to dovetail through inputs. So okay. I don't want to run out of time, but let me just give you one way to do this. So the answer is yes, you can write such a piece of code, and you can do it tonight. It's that simple. Generate all strings in sigma star. Run each through a compiler. That'll generate all valid C programs. Okay. Now you don't know how long each takes to run, and some will run forever on some inputs, and some will run in exponential time, even though they always halt. You don't know. But between all these valid C programs, all of them, all of P is covered. How many understand that part? Okay. Now the problem is it's covered lots of things besides P. It also covers exponential time and super exponential time and triply exponential space. And you want to get rid of all those. So separately, dovetail through all polynomials, n squared, n cubed, n to the fourth, n to the fifth, and so on. So take all programs and all polynomials and dovetail through all of them. And for each program and each polynomial in this dovetailing pairing of programs and polynomials, do what?
you check that with respect to the input size, you check that it ran the time of that polynomial.
Yes. Force that polynomial to be a terminating clock on that program. Hardwire that polynomial into the program that if that program doesn't stop on its own within that time, it gets aborted. And it stops by force. How many see what's going to happen here? Yeah. So now, when you start marrying all these clocks to all these arbitrary programs, all you get is polynomial time running programs. So now you don't get programs that run exponentially or that run forever or don't halt, or you only get programs that run within polynomial time. Now, why do you get all of P now? Maybe this is only part of P.
You will eventually run every program for every polynomial.
Exactly. So if there's some program that runs in time n cubed, if you put a clock of n squared on it, it would artificially abort it and mess up its operation. How many see that? But if you put a clock of n to the fifth on it, it'll work. And it will terminate before the clock runs out every single time, because the clock is more generous than its own running time. So you'll get all of P. And there's a little bit of a caveat here you got to do also that I didn't mention yet.
What about the constant?
Yes. What about the constant? Because a million n squared is bigger than 5n cubed for a lot of small n. What about those constants? How many see that there's a problem with constants here? Yeah, how do you solve that?
Cross the polynomials with a set of natural numbers.
Dovetail through all the constants too. So do a triple dovetail. Polynomials, integer constants, and programs, and for every triple, generate that program. It runs in that polynomial times that constant imposed on that program, and now you've got it covered. You got all constants covered. Very good insight. Question back there.
So how do you construct a timer? Like we have no big O notation is natural to human beings, but in terms of
It's an exact timer. With that constant, with that polynomial, you don't have to worry about the big O. because all constants will be included eventually for that very same polynomial over all programs. It's a triple dovetailing. All constants on one axis, all programs on another, and all polynomials on the third, and every combination of each, dovetailing out. So if 5n squared won't cut it, because the program runs in 10n squared, eventually you'll run 20n squared on that same program, and that one, the clock will never be activated. It will stop on its own accord.
But when you do dovetailing, you only go through a point once, right? What if you missed, like for example, you assigned n squared to a program that's supposed to run n to the third, n cubed?
But you'll also assign n to the fourth to the same program, and n to the fifth to the same program. And for n squared, you won't just assign it 1n squared, you'll assign it 2n squared, 3n squared, 4n squared, 5n squared to the same program. That's the beauty of dovetailing. It picks every combination of program, polynomial, and constant, and spit them all out. So you're spitting out only things in P, and you're spitting out all of P. No more, no less. And how many see you can write this program today, this evening? It's not that hard. It's not something that will take 1,000,000 lines of code. You call a compiler as a subroutine to just determine the programs, but the other two loops with the polynomial and the constant, that's trivial. And imposing a clock on a program is just instrumenting it to abort it when the clock ticks beyond the counter. That's an easy modification to a piece of code, right? After every statement in the code, put a counter clicks up by 1. And when that counter exceeds the clock, have it abort.
So is this program a enumerator to all the solutions to P's element?
Yes, it's an enumerator. They'll produce programs that'll cover all of P and nothing but P.
Can we make it two enumerators in lexicographic to make it a decider?
That's different than saying, so quick sort will be one of those programs. How many see that? So will Dijkstra's shortest path. So will Prim. So will Kruskal. So will matrix multiplication. So will linear programming. They'll all be on this list. But here's the problem. They'll all be on this list an infinite number of times with larger and larger clocks that never kick in. And you can't tell which is which. And it's undecidable to tell if a program sorts or doesn't sort. Although all possible ways to sort in polynomial time will be on this list. You just can't tell which is which. But that's not what I asked you to do, is tell which is which. I just asked you to produce a list that will cover all of P and nothing but P. And we've done that. And that piece of code exists because we just described how it works and we can just implement it. Yeah.
Instead of crossing the polynomials with with the natural numbers, could you also use a finite field, the Galois field, and which implicitly has coefficients in them, or Pascal's triangle, where at each level you can try a bunch of coefficients?
Well, as long as it subsumes what we just described, maybe. So you don't have to try every coefficient, or even every polynomial.
Yeah.
You don't have to try linear, quadratic, cubic. You just skip every 10th one. That'll work too. How many see that? Just skip every 50th exponent. It can only take coefficients that are powers of 2. Take coefficient being 10, 100, or powers of 10. 10, 100, a million, a billion, a trillion. You don't have to get every last one, because the bigger one will subsume the smaller ones, and you'll still be okay. You'll just get larger clocks that don't run out, but are still polynomial times. And that's fine too. Yeah.
I have two questions.
Yeah.
First one is, if you assume that I have a constant of, the algorithm takes constant time, for example, 1,000. And if I have 10n squared also is equivalent to 1,000, if for n is equal to 10. How do you know whether I have to put it in this or that?
You do both. This algorithm marries every algorithm with every polynomial with every coefficient combination.
So it is can you consider the one you're dovetailing on to be, the polynomial you're dovetailing on to be the maximum possibility of the previous one?
No, just the next one in the list.
If
So there'll be two classes of codes coming on this list. One class of codes will stop on their own accord without their clocks ever triggering their demise. How many see that? Okay. The other class will be cut short. But a program that runs in polynomial time that gets cut short before it terminates naturally still solves some problem, just not the original one. How many see that? And that problem is also in P. It's just not the problem that was intended to be solved by that original piece of code without the clock. So let's say you run merge sort. And I let you run merge sort and you're still running and running and running and I say, just stop. In the middle of running. Before you even finish sorting the input, you did something with it. I don't care what, but whatever it is you did, it's some function over the input, and that function you just computed in polynomial time, because I stopped you before you were going to stop on your own, and you were going to stop in polynomial time anyway. So I forced you to solve a different problem besides sorting. How many see that? It's kind of a cruel thing to do to a program, but not about code ethics here. We're just about making things work, right? And this works. Yeah. You're not using any inputs on the programs. You're just spitting out their codes. You're not running them.
Well, like when you test them against the runtime.
You're not testing them. I'm generating internally all valid programs, and for each valid program that I generate, I take its code. I'm not running its code. I'm taking its code and hardwiring a clock into that code that will abort it artificially if it doesn't abort on its own, given any input that you give it later on. But we're not running it right now. We're just spitting it out. We're compiling it and spitting out the programs itself. We're not running anything. The only thing we're running is this generator of programs. The programs themselves aren't running. They're static. They're being listed. So I grant you, this is an abstract, this is a pretty abstract problem. And now, you see why I chose not to put it on the midterm, probably much to your relief. But I just wanted you to know, how these things work. Let me give you, so any more questions? I want to give you another problem, then we'll have the Ask Me Anything session. Everybody good with this so far? Okay. So, I mean, it's a Jedi trick to do this, Take all clocks, marry them with all codes, and take all constants, and do a triple dovetailing, and you got all of P. All right, another Jedi trick. So, let's say somebody proves that P is equal to NP tomorrow. But it's an existence proof. It's not a practical proof. In other words, they don't come up with a polynomial time algorithm for SAT. They're just some sort of an existence proof that the two classes are the same class. And you can easily, we have many such proofs all over the place in mathematics. We can prove that there's a prime bigger than a googolplex. Right? How many? No, there's a prime bigger than a googolplex. That doesn't mean you can write one down right now. Okay, although you know it exists. You can come up with an algorithm that will discover it one day by running long enough, but it'll take longer than the lifetime of the universe. But right now, you can't write a prime down bigger than a googolplex, even though you for sure know one is out there. All right, so keep that in mind. All right, so let's say somebody proves that P is equal to NP, but their proof did not include a polynomial time algorithm for SAT, or three-colorability, or any other NP-complete problem. It's just an existence proof that the two classes are the same. Write down a piece of code right now that if a proof like that came along, that piece of code will be a polynomial time algorithm that solves SAT. And by the way, you can do this right now without knowing that P is equal to NP. You can write right now a piece of code that's a SAT solver that has the following property. If P is equal to NP, it'll run in polynomial time and identify all yes instances in polynomial time, all yes instances of SAT in polynomial time. Let's even say that on the no instances, I don't care what it does. But on the yes instances, it will always flag them down and identify them in polynomial time. Okay. If P is equal to NP. If P is not equal to NP, this piece of code will still do this job, but it can take an exponential time to run. So I'm asking you to do something very esoteric. write down tonight, a piece of code that will correctly solve SAT, correctly identify all the S instances in polynomial time. If P is equal to NP. If P is not equal to NP, all bets are off and it could run in exponential time. But it still solves SAT correctly. How many understand the spec? Okay. How many think it's possible to do? So let me tell you, it is possible to do. So you were right. How many can do this? Okay. How would you do it?
Can you search over those programs that we just generated for P? If P is equal to NP, we know if somewhere we hit the SAT problem.
Mm-hmm.
So, and we know the order of that problem, which we found that in your dovetail, three-dimensional dovetail.
Yeah.
So, we actually found an algorithm for SAT problem, and we know the exact polynomial order of that algorithm.
And how do you know which one of those long lists of codes solves SAT?
So we generated each problem, and we
Yes, it's out there, but which one is it? And how do you get a SAT solution from it if you don't even know which one it is? All you know is that it's one of those. You see, he's on the right track. He's saying, you know, just a minute ago we had a long list of codes that solve all of P. And one of them is a SAT solver. If P is equal to NP, all of NP is equal to P, and one of those will solve SAT in polynomial time. But how do you actually use it to solve a SAT instance if you don't know which it is? And how long will it take?
You can try all of them and use them as an optimizer and then check the
Yes. So take every program, every decider on this list, and convert it to an optimizer by playing 20 questions with it, and run all of them in a dovetailing fashion on that instance of SAT that you're trying to solve in polynomial time. And many of them will solve it incorrectly. Many of them will not even be SAT solvers. They'll be sorters, they'll be searchers, they'll be web browser, who knows what they'll be. And who knows what they'll do with a SAT instance that you give it. But among them, there'll be a true SAT solver and one that runs in polynomial time, because P is equal to NP, by assumption. And when it gives you the answer, just like when anything else gives you the answer yes, you will convert that decider into an optimizer, play 20 questions, and extract the actual satisfying assignment from it, and then what? Check it to see if it's really a satisfying assignment to the instance that you had in mind. All these other bogus programs, the ones that sort and web browse and do other things, and they'll say yes too, but those yeses are bogus, and a lot of the no's are bogus too. But each one, you'll treat it as as a decider, convert it to an optimizer, and eventually you'll hit the decider for true SAT in polynomial time as many times as necessary to get the answer for which you'll check, and then you'll know, and then you'll say, okay, I got it. Here's a satisfying assignment. How long will this take to run? Because you're going through a lot of programs. Why polynomial? This program could be Google to the Google to the Googleplex to factorial.
Because each process takes polynomial time or less.
So because you're running the set of dovetailing technically through the set of polynomial time bounded
Yes.
programs, then it's technically the addition of those or some composition of them in the runtime, and your worst case runtime would be the halting time of the last one.
Let me ask you this. Where on this long list is this SAT solver that we're trying to find? What's its index as a function of? It's a constant. Finally, it's a constant on this list. It's at a fixed position, and it doesn't matter if there's a Googleplex or a Googleplex or Googleplex quantity factorial Googleplex times, that constant is that large. It doesn't matter. It's a constant. And it's fixed, and it's staying there. And eventually you'll hit it, and everything before it is one big constant overhead before you got to it, and ran it for long enough to solve that SAT instance for you, and then you'll know. So if P is equal to NP, you automatically have a polynomial time SAT solver just from knowing that. And you don't even have to know it. This piece of code we can construct without knowing whether P is equal to NP. How many get that? So we can construct this piece of code blindly right now today. It's not hard to do. It's just a big dovetailing, giant triple loop, plus the decider versus optimizer thing thrown on top of that. And this piece of code will be a SAT solver that runs in polynomial time if and only if p is equal to np. But this piece of code exists right now. Not only that, you can write it down right now, tonight. And this may be it. You just won't know until somebody finally proves it, how fast it runs or not. So its runtime depends on this open question, actually. But the point is, not only it exists, you can write it down right now. So this is an interesting situation. Now, of course, that constant will be huge. So if we write it right now and actually try to run it, and actually it will take a lot longer than lifetime of the universe, and that's an understatement, because the constant is so large. Yeah.
You also said that if p is not equal to np, this program can still solve set problem, but it won't be in polynomial time. How do we know that if p is not equal to np, because the program we just described will solve all the problems in p, right?
So,
p is not equal to np,
well,
guarantee
we described how to list out all programs that solve all problems in P between them. In other words, each program solves a different problem in P. And many of them solve the same problem in P also. That's not a contradiction. So we described a method to find one that actually solves SAT in polynomial time if P is equal to NP. And if P is not equal to NP, this will still correctly solve SAT, but it will take exponential time to run. Because on the side, we'll just solve it the hard way, brute force. So we'll be solving P is equal to, we'll be solving SAT either way, correctly. Either brute force and in parallel do this process we just described, and one of them will finish first. And the one that finishes first will give us the right answer. So we'll always get the right answer to SAT, except whether we'll get it in polynomial time or exponential time depends on whether P is equal to NP.
But isn't that problem only generates solutions which solve problems in p in polynomial time, right?
Yes. But if P is equal to NP, all of NP gets solved in polynomial
Right,
time,
yeah.
including SAT. So SAT will be one of those.
But if p is not equal to np,
But we're saying if it is.
yeah, I understand that.
If it's not equal to NP, then this will run in exponential time, but still give us the right answer. So you won't be wrong, you'll just be slow. So whether this algorithm we just described correctly, not correctly because it's always correct, whether it's efficiently solves SAT or not depends on whether P is equal to NP. So we just constructed an algorithm whose runtime depends on this open problem. Interesting. Interesting that we can even do that. Right. Okay, anything else for now? So, by the way, I didn't bother the undergraduates with any of this. This is graduate level stuff, right? Yeah.
Are there other like problems for which the runtime of the existing algorithm depends on like?
Yes, you can construct arbitrary things like this. You can do the same thing for p-space complete problems, for x-space. In fact, there's even an algorithm whose runtime depends on the Riemann hypothesis being true.
Miller-Rabbit.
Yeah, which is nothing to do with runtimes or non-determinism. It's just about some some function, and a pretty simple function, right? I mean, simple in form, not in meaning and consequences. Yeah, so you can have all sorts of weird things. Okay, so I promised to ask me anything, so let's switch gears and ask me anything you want. What do you want to know? Yeah. Uh-oh.
Any animal and turn it into like a cat-sized version of that animal. By cat, I mean like a domestic cat. Which one would be the cutest?
I don't know. I always wanted like a pet dinosaur or something, but maybe a tiny little T-Rex, one that can't really eat you or harm you, but that's kind of subjective. I don't know what's the cutest. I used to have a lot of pets: cats, dogs, fish. But cuteness is in the eye of the beholder, right? Some people swear that their pet tarantula is cute. Others can't see that. So anyway, You know, if I can have a pet, I'd want a little dinosaur. Actually, I think that would be pretty cute. That'll be cute to me. I mean, your mileage may vary, but and keep it small. I don't want one the size of this building. You know. Oh, non-extinct. What's that? Crocodile. Actually,
Or keep in mind that this allows us scaling up, right? You could ask for a cat-sized tardigrade.
A cat-sized fish.
cat-sized fish.
I think referring to cat.
Or just a fish or like a shark.
Actually, I like tardigrades. You know, water bears, tardigrades. I mean, they're small. But tardigrades have very interesting properties. I'm going to hear of tardigrades, or there's something called water bears. So they can withstand radiation that will 1,000 times lethal to humans. You know, 1,000 times more lethal than radiation that will kill humans. They can withstand extreme heat, extreme cold. They can be frozen for arbitrary long periods and then thawed out and as if nothing happened. They can withstand vacuum of space for arbitrary long periods. And they're still around today. You can find them in almost every water pond. So I mean, I have a lot of respect for that animal for all this ability to survive. You know, it's not quite as cuddly as a cat. It looks pretty cute when you look at pictures of tardigrades do a Google search images on tardigrades. There were about 6 massive extinction events over the last 500 million years. The last one killed all the dinosaurs. That was about 65 million years ago. There were about 5 others, mass extinction events over the last 500 million years that killed most of the species on Earth. The tardigrades survived all 6. And they're still here, and they haven't changed, which means evolutionarily, they're incredibly fit. So, so in terms of animals, which I find, you know, very fascinating, and I have a lot of respect for, you know, that's, you know, wouldn't make a great pet because it's tiny, and you know, but you look under a microscope, they're very cute, which means there won't be a large overhead in taking care of them, right? Think about it. You know, taking care of tardigrades, you don't have to do anything.
Yeah, I mean, you have several cat tardigrades as right now.
Yeah, they're all over the place. You know, it's probably a few in my hot tub. You know, and you don't have to take care of them because no matter what you do, they'll still survive. So you're good. You know, you don't even have to feed them.
What if you didn't like it anymore? You wanted to get rid of it?
Well, I recently read an article actually that said that researchers were unable to even theoretically cause them cause them to go extinct. So.
Yeah. So if you squash them, they'll die. I mean, they're not invulnerable like Superman is invulnerable. You know, that's not what they are. They're not invulnerable to, you know, being squashed. They'll go splat. You know. I mean, but if you try to radiate them or pressure them or vacuum them, you know, arbitrary, you know, near perfect vacuum, or boil them to 200 or 300 degrees, or freeze them to, you know, cryogenic temperature, that won't kill them. They're just going to suspend animation state and then revivify when conditions are okay again. If you dehydrate them, if you don't give them any water for 10 years, they'll become almost like dehydrated kind of state. And then when you add water, they'll hydrate again, and as if nothing happened after decades of just no water. So they're very hard to kill in any other way other than just, you know, squashing them with a paperweight. That will kill them. But that's, you know, everything. They're extremely survivable. Anyway, more questions. I don't want to spend a whole hour on tardigrades.
Who's the most interesting person you know, and what makes this field very interesting?
The most
Interesting person.
The most interesting person I know? That I personally know, or like, you know, Stephen Hawking was pretty interesting. I never met him though. Person? You know, people that I met actually or know personally? I'm not sure. You know, the most. You know, there's a commercial, the most interesting man in the world, right? But it's kind of a misnomer, right? It's pretty funny. Person. It's hard for me to say the most interesting. I know some interesting people, like Morgan Freeman is pretty interesting. I happen to know him personally, but I don't know. You know, the most interesting. It's hard to quantify that. Don't know. But if I had to go to people that I didn't meet, Stephen Hawking, if you go to people who are no longer alive, well, Stephen Hawking passed recently. Albert Einstein was pretty amazing. Richard Feynman I met once actually. He gave a talk at UCLA when I was a student there, 1988, right before or 1987, I think, right before he passed away from cancer, like a year before. It was fascinating, Richard Feynman, and I didn't meet him, so it was my buddy, but I did meet him. Alonzo Church, I met him actually, Alan Turing's advisor. Again, I was a graduate student at UCLA. It was 91. He gave a lecture about the paradox of the name relation, and it was amazing to watch him. He outlived every last one of his contemporaries and every last one of his students, and or his students. I mean, he was Alan Turing's advisor in 1930s, early 30s, and this was 90s. And yeah, I suppose. Yeah, but that was amazing to watch. That was fascinating. To see a 95-year-old talk, lucidly, legibly, interestingly, intellectually, and doing research and publishing all, to the very end. That was pretty cool. I met Edgar Dijkstra, Dijkstra's algorithm fame.
I heard he's a jerk.
Yeah, well, was a jerk. He's deceased. Yeah, let's not speak ill of the dead, but yeah, it was kind of strange character. So again, he gave a talk at UCLA, and he came into the talk, and he introduces him, and he's a Turing Award winner, and Dijkstra's algorithm, and he invented semaphores and mutual exclusion. A lot of things are due to him, and he comes in and he stands there, and he looks very sternly at the crowd, and he looks at the board, and he's after his introduction, he's supposed to, and he doesn't start speaking, and finally somebody says, Professor Dijkstra, is anything the matter? And he goes, yes, the board is not erased. He was waiting for somebody to, and he didn't say anything. He was just waiting, for like 2 minutes, which seems like an infinite amount of time when everybody's quiet, waiting for him to start. And so finally, we were kind of in shock that this has happened. So finally, some meek graduate student goes up and erases the board very dutifully, and then he started the talk, and then it went downhill from there. But so that was an interesting character. Yeah, I mean, when you do great things, people give you some passes for being a jerk. Doesn't mean you should be a jerk. Try not to. It's better not to. Yeah, I mean, Steve Jobs did some amazing things, but he was a bit of a jerk himself too. We weren't sure. We were afraid. We were afraid to ask. Frankly, we didn't want to, tangle up with him. We just erased the board and let him start. Not sure why. So that was mysterious. Yeah.
Do you think it would be worthwhile to try to build settlements on the moon?
Yes, simply because of proof of concept, to see if we can do it, what the hurdles are, just as a challenge. I don't think we'll get huge commercial value from it unless we find some really interesting minerals that are not available anywhere else, or find huge diamond deposits. And I don't mean diamonds like for jewelry or stuff, but diamonds have very interesting properties as materials. In fact, we believe that the core of Jupiter and Saturn are one giant diamond, larger than the Earth. Simply because it's just carbon squeezed into the allotrope of diamond, which is just carbon in a matrix, in a crystalline matrix. That's all. But anyway, yeah, going to the moon has its own benefits. Plus, there's intangible benefits. Like, you're not old enough to remember, most of you. I remember the first lunar landing, and I was just a kid. It was 1969, Apollo 11. And we all looked up, and we all looked at the TVs, and Neil Armstrong, one small step for man, and all that stuff, and it was very inspiring. And millions of people all over the world, millions of children all over the world became scientists because they saw this happening, and they thought it was so cool. So it has a very broad impact, intangible impact that you can measure in dollars and cents and political brownie points.
But like in comparison to say like Mars, I mean.
We should go both, but one doesn't exclude the other.
Well, I mean,
we should do
I
both.
know, it's just that
Yeah.
to build settlements in places. I imagine Mars would be a little more feasible than the moon long term for humans because
They both have different challenges. The moon has water, actually. How many knew that? The moon has water. They're hidden, like, in dark places where the sun doesn't shine because there's a big crater and it's all like in the shadow. But if we can get to that water, it'll make, and use sunlight to dissociate the hydrogen from the oxygen. The oxygen we can breathe. The hydrogen we can use as rocket fuel or whatever. And there might be ways to sustain ourselves on the moon. It's going to be harsh, very harsh, for sure. Well, you saw what Matt Damon did on Mars, right? I mean, a sack of potatoes got him through like 2 years. That's pretty good. I think he used poo as fertilizer, though, didn't he? Your mileage may vary, but so just as an exercise in problem solving, it has a lot of value. And just to say we did it and have kids just look up, in awe and wonderment, that has tremendous value too, because millions of them will become scientists just from watching these amazing accomplishments. So if you look at the big picture, it's really worthwhile doing. Now, as a practical matter, if we mess up the Earth so bad that it becomes uninhabitable and that, like, the moon is our only option, we're screwed. That's not going to happen. But as an exercise in problem solving and cool factor, let's have a moon base. In fact, in 2001, Space Odyssey, it shows a moon base, and there's a show called Space 1999. I remember that from the 70s. That showed a moon base too, the moon base alpha and whatever. So we for sure we thought we'll have moon bases by now, and here we are 20 years after 2001 deadline from Stanley Kubrick and Arthur C. Clarke, and we haven't gone to the moon again. The last time we've been to the moon is when? It's early 70s. How many humans have set foot on the moon? There were six lunar landings. Each one had 2 astronauts in the lunar module, and they took turns. So that 12 people, 12 humans ever set foot on the moon, and that's it. And it only happened late 60s, early 70s, and that's it. We thought it'd be true about hundreds of people by now. But how many countries have been to the moon? Just one. How many entities have put, spacecraft into space? Americans, obviously, the Russians, the Chinese, Indians, and Elon Musk. So, yeah, exactly.
Blue Origin just launched a rocket successfully.
Not orbital flight. It's a huge difference. Yeah, Jeff Bezos and Elon Musk have this kind of tweeter back and forth, and Jeff Bezos says, "Yeah, me too." No, not him too. Not orbital flight. And orbital flight, you have to go 10 times as fast, and you need 100 times the energy. It's not at all the same thing. The technical hurdles are universes apart. Yeah, but anyway, I digress. What else?
You could ask one question of one of the historical figures we talked about in class. Who would it be?
I don't know, but it'd be nice to have whole conversations rather than one questions. You don't get much from a single question, right? But it'd be nice to have conversations, with people like Newton, and Aristotle. It'd be really cool to have a long lunch with Aristotle or Plato, and just shoot the breeze, and if nothing else, just give them a few hints of where this is all going and what blow their mind, about. Just show them an iPhone or something, Yeah, or meet Nikola Tesla and take him to drive in a Model S, He'll probably be upset that they used his name without paying him royalties, But yeah, that'd be really cool. There's actually a science fiction story about some person built a time machine and went back to meet Newton and gave him a calculator, like a handheld calculator, and figured, wow, if he invented calculus without even any electronics or calculators, or imagine what it would do if he had a calculator. So Newton starts playing with it, and he punches some random numbers to do multiplications and square roots, and all of a sudden it comes out 666 as the answer, just randomly. And he was kind of a religious guy, so 666, the number of the devil. So he was so distraught and and alarmed by this, that he thought it was some sort of a devil device, so he put it aside and dropped math and physics and science and went to divinity instead and became a priest, and we never had calculus or anything else for that matter that's built on top of calculus, which is most of science. So anyway, so that's one of those unintended consequences, kind of funky science fiction stories. So you have to be careful, you know, when you talk to these old people, you know, about Leibniz. Yeah. Yeah. All right. Yeah. What do you say?
Who's your favorite political leader?
Political leader?
Alive.
There's not a whole lot to choose from, you know. So you know, I like the notion of a philosopher king, kind of, you know, the Greek notion of the philosopher king, somebody who's wise and doesn't abuse their power, or her or his power, and doesn't do it, you know, kind of a reluctant leader that doesn't really want to do it to get off on the power and pushing people around. But that's very few and far between. Most people, modern leaders, aren't in that category. In this country, probably Washington was the closest, you know, George Washington. First of all, he didn't want to serve as president. They had to beg him and, you know, cajole him and you know, plead with him for a long time before he said, fine, okay, I'll do it. And then his second term came around, and again, he wanted to step down, and they had to beg him again, and he served 2 terms. And they wanted to serve a third. There was no term limits back then. Remember, this was kind of up for grabs. And after 2 terms, he said, no way, I'm stepping down, and he just walked away from this and went back to his farm. And that was amazing and commendable. No modern leader I can see doing this. Given a chance to serve longer, they'll say, no, thank you, I've done enough. It's time for new blood and new ideas and new leadership. And you know, nobody should serve more than some limited amount of time. It's not healthy. It leads to dictatorships and abuses. I don't see anybody today alive that's in charge of anything having this attitude. Sad. In fact, they have the opposite attitude. They claw and cajole and lie and cheat their way to the top, and then they try to stay as much as they can. And you know, then they try to change their own constitution to remove term limits, if there's examples of that recently, and on and on and on. And that's not just alarming; it's unimpressive. You know, it's the opposite of leadership. It's not good.
We can't trust humans, so we have to like build a stronger system.
Yeah, you know, so the Greeks invented democracy per se, and we've had lots of iterations of democracy and other kinds of governments, and we still don't have it right. You know, and if you watch the news lately, you know, we have it terribly wrong, actually, in some ways. But on the other hand, it's one of the best systems we have. As flawed as democracy is, and it's inefficient as it is, because everybody has a say, so they all jump in, and it's very inefficient because everybody pushes and pulls in all directions, and it's still pretty good on average, given what happens when you don't have democracy, like world wars and genocides. You know, that's worse. That's worse than just bickering and you know, porn stars getting hush money. But I digress. You know, it's not setting the standard of comparison very high. But you know, we've had some terrible events in human history that most of them came not from democracies. You know, they came from dictatorships and fascism and Nazism and all sorts of nasty, non-democratic situations. Yeah.
Do you think there exists an ethical philosophy which cannot be abused?
By definition, everything can be abused. I mean, every tool can be misused for something else. And humans are pretty good at finding all these loopholes, right? I mean, when social media came around, we thought, oh, it's wonderful, and everybody can communicate and share photos and keep track of their families and friends. And now we have, you know, Facebook, full, you know, fake news, and you know, it's used to overthrow elections and blah blah blah. Everything could be misused if you put your mind to it, and that's your intention. You know, you can't legislate good behavior. You can have all the laws you want, but if somebody wants to do something nasty, there's no way to intervene before it happens. You can intervene after it happens and arrest them, incarcerate them, try them, judge them, jail them, but that's not preventing it from happening. That's just some afterthought after the fact. You know, so that's why I don't like, you know, encoding good behavior as big sets of rules. You know, it has to come from within, you know, and the way to do that is by educating people and informing them about history and what happens when people do bad things, and up to and including genocides and horrible world wars and stuff. And, you know, good behavior doesn't come from a list of commandments. You know, when you see a puppy and you're wondering whether to kick the puppy or not, you don't say, let's see, I feel like kicking the puppy, but it may be wrong. Let me check. Here's my list of 10 commandments. Does it say anywhere here not to kick the puppy? No? Okay, I guess wham. That doesn't work, you know. And I mean that metaphorically. It's not just about kicking puppies. It's about doing anything. So you can have long lists of rules, and then even incentive structures are kind of off kilter. You know, if the only reason you do something good or don't do something bad is because you're worried about punishment or you're after a reward, that's not a great reason to do good or not do bad. You know, most of the time it's pretty clear what's right and wrong, what's fair or not. You know, we don't need long lists of rules to go down the list and see, oh, this is good. No, this is bad. Don't punch somebody in the face. That's bad. You know, wave them hello. That's good. So it doesn't work that way. You know, people and humans and psychology doesn't work. And whenever you try to codify good behavior as a long list of rules, whether they're laws or religious edicts or other, or you know all sorts of other lists, and you know, it backfires. And people look for loopholes also. You know, if you say everything on the list is good and whatever is not on the list is bad, they'll find all sorts of ways to do bad things, skirting what's on the list and what's not on the list. People tend to start thinking like lawyers when you give them long lists.
But what if there's no list, then everything will be anarchy.
No, it's not one or the other. You know, I'm not saying up for grabs, anything goes. No, I mean, you know, I think most reasonable people can agree on what's fair or not, what's right or wrong, you know, what's harmful and what's beneficial. And, you know, we can split the differences, but it's not that complicated. You know, I mean, coming up to somebody and just killing them where they stand, most people will agree that's wrong, and that's not fair, and it shouldn't be done, and that's harmful, and that's not okay, regardless of what the law says or doesn't say.
But even though you have those punishments, people will still try to find loopholes, and they will still trying to, like, just imagine without any kind of rules. I think it would be worse. Build those rules.
It may be right. It may be worse right now. I agree. But in the long term, in a few centuries, it may not be as necessary as it is today. You know, one of the reasons people act badly today is because they're desperate. There's not enough resources, not enough food, not enough shelter, not enough money, not enough. But you know, if robots, you know, rise and provide for us everything we need, if there was no such thing as jobs, I mean, no such thing as money. Why do we have money even? It's an accounting mechanism to make sure everybody contributes, because some things need to be done and there's not enough manpower. And so, but if robots did all that stuff, you know, we wouldn't need to worry about money. Money wouldn't even exist. It wouldn't make sense to have it. Jobs wouldn't exist per se. You do whatever it is you like to do and have a lot of hobbies, and you know, and then people wouldn't be so desperate, and it wouldn't be so hungry and needy, and that creates a lot of strife, and you know, that leads to a lot of wars even, you know, contention for resources. If everybody had everything they needed, there'll be a lot less strife. People can afford to be nicer. It's not communism. It's high technology. You know, so the word communism has a lot of baggage associated with it. Even in communist countries, you know, it has a lot of baggage. Never mind in other countries.
But yeah, but you were describing it sounds a lot like our textbook back in China.
No, because I'm talking about people won't have to toil very hard to get what they need.
Right now.
Robots will do all that.
Right,
you know, and robots can also protect people against other people who may mean them harm. You know, so I'm talking about some utopia that is nowhere near, you know, this present day. You know, I'm talking about something that's centuries from now. Right now, there's a lot of strife. There's not enough resources. Many people are starving. You know, if somebody's starving or watches their kids starving, all bets are off of what they're going to do in the next hour or the next day. You know. But if people aren't desperate, and if it's enough to go around, and robots just do everything for free, and plenty of it, we'll be able to afford to be nicer. Also consider a lot. Eventually, we should get rid of our aggressive tendencies. So aggression is what got us to this point in history. 100,000 years ago, aggression had a lot of evolutionarily survival value. If you were aggressive, you could protect yourself and your brood and your offsprings and against saber-toothed tigers and raptors or whatever was crawling around in those days and trying to make lunch out of you. If you were aggressive, you had a higher propensity to survive. So all of us today that are here talking are descendants of the aggressive ones. The meek ones never had children. They died at a very young age as lunch for other predators. So by definition, all of us have aggressive tendencies built into our genes. It's hardwired. Luckily, we also have means of reasoning about it, and creating philosophy and science and psychology, and not always be prisoners and slaves to our aggressive tendencies. So we try to find other ways for our aggressive tendencies, like boxing and football, and reality TV, and people just being nasty to each other. And if you think about what boxing is, two people bashing each other's faces in until one of them gets knocked out unconscious. They call it sport. I don't call it sport. It's hostility disguised as sport. So are most sports today. They're proxies for war. Don't get me wrong. It's better to have a boxing match than a genocide or a shooting war. But they both come from the same place. Aggressive tendencies. So one day we'll have to get rid of it, one way or another. But it's hard because it's hardwired into us, and by definition it has to be. It's what got us to survive to this point. But right now, aggression is no longer an advantage. It's a dysfunction.
What if we're facing some alien life who's trying to make us lunch?
If we face aliens, we won't have a chance. It'll be over in milliseconds. There's no point resisting. We'll never even see it coming. I mean, if you want to destroy a bunch of ants crawling around, there's nothing they can do to stop you. They won't even see it coming. They'll be gone, and that'll be the end of it.
What if we're facing a group of aliens that's like the same level as us, maybe in the 5,000 years later?
They won't be the same level as us, simply because if you pick two random numbers between 1 and a million, what are the chances they'll be equal to each other, or within two of each other? I mean, we haven't been around for very long. Only a few 50,000 or 100,000 years. If you met if we met one of our ancestors from 100,000 years, we wouldn't recognize them as human. They'll look like more like a gorilla or a chimpanzee rather than we look like today. So it's because we haven't been around for so long, and life existed for 1 billion years just on this planet, and on other planets it may have existed for several billion years. Whoever it is we meet, chances are will be a lot more advanced than us. So advanced we won't even understand their technology and science and their insight. It will not be a contest like in one of those Will Smith movies or Independence Day or whatever. Those Hollywood movies need to create a tension for 2 hours and almost equal match so that it'll make a nice plot. But if this was a realistic scenario, within the first 3 seconds of the movie, one would destroy the other, and then the lights would come on and the credits would roll, and everybody would want their money back because it wouldn't be very entertaining. But in reality, that's what it would look like. It wouldn't be a prolonged, almost equal fight. No, it'd be more like between us and ants. Sadly for us, I guess. And the reason I say we will be the ants is simply because we haven't been around for very long. Imagine what our species will look like, what technology we'll have in 10,000 years, or 10 million years. And even 10 million years is not very long at all on cosmic scales. Most of what we invented only was invented in the last 50 years or 100 years at most. That's it. If you compress the entire history of the planet to a 24-hour period, humans appeared in the last second of the last minute of the last hour. That's it. So no, it won't be a fair fight, and we'll be on the losing end most likely. Now it doesn't have to be a fight. Just like when we see algae and moss and ants, we don't always just rush to squash them as a first instinct, even though we're pretty aggressive. So hopefully they will be even less aggressive than that.
Maybe they will make us pass.
Yeah, chances are they won't even notice us. You know, just like you don't notice every little moss and leaf and insect that you go across when you walk across the campus. You know, I mean, occasionally you see one, it's like, oh, whatever. You keep walking. You know, you don't start harassing it. Right? So hopefully, we'll be okay. You know, plus the distances are so large in the universe. You know, the closest star is 4 light years. That's just the closest star. You know, in current rocket speeds, it's 100,000 years just to get there at the fastest rocket we have. In 100,000 years, if we send humans there, and they come back in 200,000 years, they won't recognize any of us due to just natural evolution. And that's just the closest star. You know, the galaxy is 100,000 light years across. The nearest galaxy is 2 million light years. That's Andromeda. And that's just the closest galaxy to us. And there's trillions of other galaxies out there. So just the distances make it unlikely that any two, you know, independently evolved species will find each other very likely or very readily or, you know, very often. You know, and it's hard to find life in the universe in general, again, because it's so large. Imagine you were on a boat in the middle of the ocean. You want to see if there's life in the ocean. You know, you take a cup, you go like this, you look at the cup, oh, it's just water, it's empty, oh, must be no life there. Okay, I'll do it again. I'll go, sail another few miles, go a cup like this, oh, no fish, nothing, oh, okay. 10 times, 100 times, you know, and then you'll conclude there's no life in the ocean. And you'd be very wrong. But the point is the ocean is very large. And we know there's plenty of life there, just not in any one cup or 1 cubic foot of water. Just, that's all. So, yeah. So it depends how you look and where. And so right now, the only way we have to look for other intelligences is radio waves or whatever their transmission mode happened to be. Right. So we can't directly, you know, even probes to Mars. We send several probes to Mars. It's very hard to create an experiment that remotely detects life or even signs of life. It's very difficult, actually, biologically speaking, chemically speaking. Especially if we don't know the basis of these life and their biology and their chemistry and so on. And even when we look for signals from, like Project SETI, right? Looks from signals from outer space, like in the movie Contact. You know, Jodie Foster plays inside. It's a real person actually. She's playing a real person that's actually alive doing Project SETI. But we're only looking at certain directions in pieces of the spectrum only for radio waves, but not for other kinds of radiations like lasers and X-rays or even gravitational. Maybe they're communicating using gravitational waves. We just finally discovered gravitational waves just a year or two ago, and only briefly, only because 2 black holes collided, and our instrument was just powered enough to detect that very large collision. That's very far away, so it was very faint. But it's hard to predict how to find these other aliens, or but the chances that that we're alone in this whole giant universe. Once you see the scale of the universe, that's why I have you watch Scale of the Universe kind of videos. You know, to think that this whole thing was like built for us and us only, and that's unlikely. You know, that's very self-serving. It's very immature. I mean, a baby thinks that this whole world revolves around them, and we go, oh, you know, because it's just a baby. But if an adult thinks that, they're a narcissist. And you may have heard of some in the news. But again, I digress. You know, so our whole species is narcissistic collectively. Our whole species is very immature and narcissistic and self-absorbed and full of itself. And we're slowly getting rid of that in small steps. We used to think that the Earth was the center of the universe. Now we know that's laughable. But that was only 300 years ago. And people were killed for saying that. And now they're no longer killed for saying that, but some people believe, you know, equivalent things to that. And it's not very likely. It's not very helpful. It's not very humble. And it doesn't encourage discovery and questioning and, you know, research. and looking at things objectively. And our species has another problem. When we don't know something, our species has a tendency to make stuff up instead of admitting that we don't know. So it's better to admit that we don't know stuff rather than to make up stories and then take them as fact. There's also some value in doing that, but in recent years and decades and in this century and going forward, it's dysfunctional. It's not particularly valuable to make stuff up and then pretend it's the truth. There's an old saying, denial ain't just a river in Egypt. But a lot of people just rather live in denial and in made up facts and stories rather than admit that they don't know and then go on searching for them. That's hard. It takes effort, education, studying, hard work, diligence. And it's uncomfortable to do that for a number of reasons. So yeah, it's easier to just believe what you're told growing up, and so we got some issues as a species, and it would be kind of quaint if these issues didn't give rise to lots of other problems, like wars and genocides. So the minute you think you have a grasp on the truth and everybody else is wrong, not too far on the heels of that, there's a holy war brewing, and people will die by the millions. And that happened many times in history, when one group thought they got it all figured out, and everybody else is off kilter at best, and just dead wrong and heretical at worst. Nasty things happen, including world wars and genocides of all kinds and ethnic cleansings, and it wasn't pretty, and it's still happening. It's so there's it's tricky business. I think in the long term, education is a solution to a lot of everything. Not to everything, but to a lot of things. If people know a lot and study a lot and thought a lot and exposed to a lot of ideas and other groups and other people and their ideas, it's hard to think you're better than the others once you know the others and they know you and you spend time with them. And just travel, just traveling around the world is very healthy and beneficial. And you see people are all mostly the same, they have the same issues, the same fears, the same insecurities, the same concerns. They all want to do well and their children to do well. And we have a lot more in common than differences. And if aliens do ever show up, they won't be able to tell the difference between us. Just like you can't tell the difference between two salmon swimming in, they'll look like salmon to you, and they'll all look the same to them. There's a famous Star Trek episode, in the old series. The Enterprise runs across some planet, and there's two planets at war with each other in the same solar system. They've been at war with each other for centuries, and they hate each other. And they send both their diplomats, their representatives, to the Enterprise, and Captain Kirk meets them both. And each one claims that the other is very different than them. They look the same to Captain Kirk, and he looks more carefully, and they have this line, bilateral symmetry, and one is white on one side and black on the other. The other species is the opposite. Instead of black on the right and white on the left, they're white on the right and black on the left, and they just hate each other over this difference. It's a show. It's an episode about bias, obviously, and it looks ridiculous to us that they're fighting over this because they look the same to us, and we can't tell the difference, and they are the same pretty much, and yet they have this bitter conflict going on for centuries, and they're killing each other off, and it's an allegory, right? We're doing the same over here to each other over really non-differences, very, very minor, tiny little differences that don't mean much and don't matter much, and it's hard to even detect those differences. So yeah, we got issues, and it comes from evolutionary times. In caveman days, it was evolutionarily advantageous to clique and clan in small groups and fight all the other groups around, because there was hardly any resources or food and shelter, and there's predators, and the predators had to eat something. So if they didn't eat the other group, they would eat you, and so you had to be very aggressive. But we're way past that now, and aggression is no longer an advantage; it's a dysfunction. So not enough people can see all that. They just cling to these impulses as if they're unchangeable, and if they're precious. They're not. We need to get rid of it, or or those impulses eventually get rid of us, one way or another. So, anyway, what else? Yeah. You want to know something about NP-completeness or something?
Which complexity class are you using?
Complexity class? I don't know. What's that?
It's a type error.
Type error. Well, you know, if I can reinterpret that as, you know, what kind of a belief or person or system I subscribe to, or, you know, class of rationality. You know, I think you know, being rational, you know, and try to be objective and rational, you know, whatever class that is. I don't know if it's decidable, but it helps just to think clearly and rationally, and, you know, not argue for your limitations. You know, if you have limitations or drawbacks or issues or problems, admit them. Don't live in denial. Don't pretend it's okay, you know, to have those. You know, try to do something about it to surmount those things. You know, to transcend those things. You know, instead of saying, oh, you know, humans are aggressive, it's okay to be aggressive. No, it's not okay. You know, we can get rid of it eventually. I'm not saying it'll happen overnight or even within a century, but, you know, in 1,000 years, there will be no wars. Let's try to make it sooner than 1,000 years. You know, and why do I think in 1,000 years there will be no wars? Because if there are wars up until then, we'll never survive 1,000 years to talk about it. Right? Einstein famously said, I don't know how World War III will be fought, but World War IV will be fought with sticks and stones. So by definition, if we survive to 1,000 years from now, there will be no wars and conflicts, or even countries. We'll just be a species on this planet trying to do the best we can. Countries are archaic, just like fiefdoms and cliques and clans are archaic. You know, nobody asks, you know, which clique are you from? Which clan are you from? You know, that would sound weird, right? One day it'll just be as weird to say, which country are you from? You know, countries are accidents of history that, you know, were necessary once to fight over scarce resources and kill everybody else who got in our way. Yeah, countries were good for that, but now it's dysfunctional. You know, so yeah. Anyway, I don't want to get too far afield on these things. Plus, I don't want to offend anybody. Really, I hope I didn't so far. You know, I just some thoughts I have. Yeah.
Given that.
Uh-oh.
Given that statement, do you think BPP will collapse into quantum? Given what you just said.
I don't know. What else? Yeah.
Given a chance to work on one of the open problems, which would you work on?
Open problems? Well, I mean, by definition, I have lots of chances to work on lots of open problems, right? I'm a professor. But you know, I try to work on open problems or on problems that have large applications or implications or benefits. So, I worked on the Steiner problem simply because everything is about connectivity, right? You can interconnect the, you know, conduits in this building, or the electrical wires, or the air conditioning ducts, or roads connect, you know, networks. So I chose to work on Steiner-type problems because their connectivity is ubiquitous to lots of other things. So I try to find kind of general things to work on, and sometimes it's more specific, but. You know, I don't have like a holy grail of a problem. I mean, sometimes I fantasize about solving P is equal to NP, but, you know, if that's not too perverse to admit, you know, but, you know, so do a lot of people. And, you know, it'd be interesting, but I can't say I devote serious time to that, you know, simply because it's not likely to happen. So you don't want to put too many eggs in that one basket that's not likely to bear fruit. Same as when you're a graduate student. You don't want to pick for your thesis some topic that's not likely to, you know, pan out in a couple of years or whatever, a few years for your dissertation, right? You know, but if I had some, good chance of success, it'll be nice to solve something like P is equal to NP type, not necessarily that one, but something equivalent, because if you come up with a good polynomial time algorithm for a large class of problems, you're hitting a lot of things at the same time. You're solving a lot of things simultaneously, and you can have a wide benefit. So for example, if somebody proved P is equal to NP, and came up with a fast algorithm for SAT, it can help cure cancer as well, because protein folding is NP-complete, and protein folding has to do with cancer behavior. It's all about proteins and how they fold. The tertiary structure of proteins in the human body cause disease or dysfunctions or genetic issues. And so if you can solve P is equal to NP, you can not just cure cancer, but solve a lot of other interesting, high-level, important, impactful problems, and that would be nice. So that's kind of how I try to pick problems, is things that will have a lot of impact, if possible. It's not always easy to predict what will have impact and what won't. Sometimes some esoteric things that you thought wasn't practical has a lot of impact and uses later on, much later on sometimes. What else?
Among the natural languages that you have encountered, which do you think is the most expressive or useful in expressing exactly what you mean? And do you think that ambiguity is useful in language beyond like poetic value?
Well, as humans, everything we do has some ambiguity in it. Almost by definition. We're very imprecise. Even when we try to reveal formal and precise, it's only in limited context, like this. So yeah, ambiguity has some value, I think. Sometimes you don't want to be very precise, especially when you express emotions and feelings and aesthetics, and in art you don't want to be particularly precise. You can, but there's value in being ambiguous. Even in movies, some movies leave a lot to interpretation of the viewer, and that's useful. It's because it can mean different things to different people, and they all can derive value from it. Where if you make it super precise, it's much more niche-y kind of audience or message you're delivering. And so even in this course, I sometimes almost use imprecision or generalizations in a constructive way. So a lot of the stuff I have on my slides and stuff I talk about, hopefully, will give you ideas beyond just complexity theory and NP-completeness and Turing machines and so on. That's I actively strive to do that. So it has educational value too, to kind of generalize and not be too niche, too precise necessarily. And there are times where we should be precise, and it's a good exercise to be precise. And sometimes we harp on the precision just to make sure we can do it, if nothing else. So it's okay not to be precise if you know how to be precise. If you have no idea how to be precise and you just talk with imprecision and ambiguity all the time, well, in the news we see people who do that all the time. It's not very effective, and it's worrisome actually. If somebody can't be precise. So yeah, it has. I agree, it has value. Keep in mind also that all these words that we use, that we're using in this conversation, we invented all these things. We use these words to describe phenomena that we did not invent. Atoms and protons and forces and gravitation and energy and mass and momentum. Those things we did not invent, but we use words that we invented and we throw them around. And there's also disconnect between the words that we use and the phenomena that we use those words to define and discuss and describe. So there's impreciseness already built into our very language. When we say electron, we don't really know what we mean, even though it's one of the more precise terms. It's not like beauty or truth or fairness or justice. Those are even less precise than electron. But nobody knows what an electron is. And there's even debate, it's not even a debate. In quantum mechanics, it's several different things. It's waves, it's particles, it's other things, depending on the context. And nobody's ever seen an electron. Nobody ever will. It's something very nebulous. So there's already imprecision built in, even when we talk about science. And that's one of the places where there's less imprecision than other things. So, yeah, imprecision and ambiguity is all over the place anyway. Yeah.
If we eventually reach like a ceiling for like the physical limits of computation, what's next in terms of like what we do as like computer scientists? Do we just focus on theory?
Well, so when you say limits of computation, you mean like
Physical.
computer speeds?
Yeah, like the architectures that we're able to construct, which given our resources.
There's always more. I mean, the human brain is very limited. First of all, by size. You know, I mean, it has to pass through the birth canal of another person, so that already limits how big the brain could be. You think about it. No, I mean, it's an evolutionary bottleneck. Artificial brains could be as large as buildings or even as large as planets, right? So there's no limit of computation per se. There's a limit to what we as a species can do individually on our own. But on the other hand, we built all these other brains. You know, these brains and larger brains, cloud computers, and eventually maybe quantum computers and beyond. So we're building prostheses for our own brains, and we're nowhere near any limits in that.
Even if there's like speed of light is a limit, even if there's like heat generated, like those.
But we just create larger assemblies of those, in terms of whole entire cloud computers that have millions or even billions of these units working in tandem. And then you can have many of those cloud computers all over the place, and even stick them on other planets or whatever. I mean, you can have nanobots that will go and descend on some planet and convert the entire thing to a computer from raw elements, one day. So you have planet-sized computers all over the place computing for us. There's no physics limits on that. I mean, yeah, the speed of light is not going to get any faster, but we can employ more and more processing power, in all sorts of ways that it's hard to do today. Actually impossible to do today, but one day it may be possible. If we get quantum computers going, that could be a cheap end run around NP-completeness too. To be determined if that will work or not. But that has a lot of potential. And if you have a quantum computer, the size of this room or the size of this building, you may not need an entire planet worth of CPUs. Something the size of this room can outdo a classical computer the size of a planet. Or the size of a galaxy even. Remains to be seen, but that has a lot of potential. In some sense, the entire universe is one big computer. All the particles are processors, and they're interacting using these laws of physics and so on. So here we are subroutines. We are all subroutines in this big computer called the universe. So in some sense, this whole reality is one giant computation unfolding, right? And within it, there's other subroutines that we built and isolate specifically, namely these boxes that we call computers. But all of this is a computer, right? So.
There was actually a guy who recently programmed Tetris on top of Conway's Game of Life.
Yeah, it's computationally universal. You can program arbitrary Turing machines using Conway Game of Life. What else? Yeah.
Have you ever taken an IQ test?
IQ test? When I was little, I had some trouble in school. So my mom, to her credit, got me to skip a grade. And before that, I had to take an IQ test to make sure I qualify. So when I was 7 or 8, I took an IQ test. Don't know what the results were. It doesn't really matter to me. But one of the questions the psychiatrist asked me, and I guess I was 7 or 8, and they said, do you read books? I said, yeah, of course I do. What have you read lately? And I said, well, I read this physics book. It talks about perpetual motion machines and how the second law of thermodynamics prevents a machine from running forever. There's heat dissipation, and nothing can run forever. Heat dissipates, energy dissipates, and a lot of attempts to run perpetual motion machines. And I went on, and he kind of looked at me like I was from Mars, and eventually he said, fine, you can skip a grade. So I read a lot of encyclopedias when I was 7, 8, 9, 10. So I know a lot about different subjects, not just computer science. And I could talk to other people about their fields pretty intelligently. That comes in very handy in a lot of scenarios, you know. I was just very curious, you know, and my original upbringing was religious, and I found that very confining. And you know, whenever somebody tells you there's only one book you need to read, be very, very suspicious of that, no matter what that one book is. You know, you can read that book, but read a lot of other things too, just to round it out, and then decide for yourself what you want to believe in, what information you want to use, and how you want to use it. So I read encyclopedias cover to cover as a kid when I was 7, 8, 9, 10, and it was very, very helpful. You know, I didn't have to take the word of adults anymore. And in fact, as a kid, I put adults to the test. You know, it's an anecdote. Once we were sitting on a balcony, I was probably 7 or 8. You know, a friend of ours was an electrician, a friend of the family, and I looked at the power pole and I saw these parallel plates made of plastic where the wires connect to the power pole. You know, and I asked, you know, what is that? And he said that it's a transformer. And I said, really? Because I read some electrical engineering books, and it seems to me like an insulator. Remember, I was 7, he was probably 30-something, right? And he said, no, I'm an electrician, trust me, it's a transformer. So I said, okay. You know, I went back to the books, I researched it, I looked it up. This was the 1960s. We had no web, I had to go to the library every time. You know, it was hard to find books. You know, I couldn't Google anything. You know, Google didn't exist. The internet didn't exist. So it turns out it was an insulator. I was right. I didn't go back to him or confront him or anything. I just said, oh, okay, interesting. I made note of that. And it happened many times with many adults, you know. And I asked them, you know, just simple questions. You know, I asked once my dad if any planets have rings around them, like sometimes you see in a cartoon or a comic book. And he said, no, of course not. You know, and you know, turns out that, you know, Saturn's got rings around it. He didn't know that. Not surprisingly, I mean, a lot of people don't know that. The rings are very nebulous and very thin, although they're wide. And I went through this process many times, and I realized, you know, adults don't know very much. And worse than that, they think they know. That's the second problem on top of the first. It's okay not to know. It's worse when you think you know and you don't. So then I realized as a kid, you know, if I want to know stuff, if I want to find stuff out, I better do due diligence myself. I better go to books, to original sources, find out, you know, dig into things and find out what's really true, what's not true, how things work, how they don't work. That was very, very valuable experience, especially for a 7, 8, 9-year-old kid. I just stopped taking people's word for it because I realized they're wrong. And I realized it's worse than they're wrong. They don't even know they're wrong. So I didn't confront them. I didn't make a big deal of it. I didn't humiliate them or anything like that. I just, you know, just let it go, but kept reading books and kept diving into knowledge and, you know, looking at encyclopedias and going to original sources, not just taking people's word for stuff. Because they just repeat to you what people told them, and they didn't bother to check if it's correct or not, or right or wrong, or makes sense or not, or they didn't put stuff to the test. They just give it to you as if, you know, it's fact. And kids usually don't know better, and it's harmful to do that to children. To just fill up their mind with stuff that is off kilter and dogmatic and just, you know, doesn't serve anybody very well, including the children or the people they interact with later on in life, or their children. They'll just keep passing it on. And so that was a very interesting revelation, very useful, you know. What was your original question, actually? Forget already.
I asked if you had taken an IQ test, which you said yes.
Yeah. So, but I answered more than that. I mean, you know, it's not about the IQ. You know, it's about learning things and finding things out, putting things to the test. You know, seeing if things make sense. You know, it's assimilating knowledge from all sources and so on. That's much more valuable than just being smart. You know, there's a lot of smart people that don't do much with their intellect, which means that they're not really all that smart. You know, they can solve trick questions on an IQ test, but nothing else. You know, that's kind of sad, actually. Also, there's something called emotional quotient. There's IQ, intelligence quotient. There's EQ, emotional quotient. EQ is more important than IQ, actually, in terms of success, having a satisfying life, reaching your goals, getting along with other people, having good relationships in your life, whether it's family or loved ones or whatever. EQ is very important. A lot of people have high IQ and lousy EQ, and they don't do very well, as smart as they are. Technically smart by passing IQ tests. So I much rather have EQ than IQ, and you're better off like that. I mean, it's better to have both. Don't get me wrong. I mean, I'm not poo-pooing intelligence, sure, but there's other things that are more highly determinant of success and happiness and good relationships and so on. And good old-fashioned hard work and diligence and perseverance, that's very important too. So a lot of people are very smart they can score very highly in an IQ test, let's put it that way, are kind of lazy and don't do much with that raw talent. And they don't get very far. They're not very successful, they don't achieve much, they're not very impressive. They can just score high in IQ tests. And there are people who work really hard and are average intelligence, who are much more impressive and successful and have much more happy lives because they're hard workers and they persevere and they don't give up, and if they get discouraged they go away and then they come back and keep going. As a determinant of success, whether it's financial success, professional success, success in relations with other people, perseverance and hard work counts for a lot more than raw IQ scores. By far, it's not even close. Again, don't get me wrong, ideally you want both. You want to score high on IQ tests and have a lot of perseverance and diligence and tenacity. Sure, then nothing will stop you. But if you have to pick one, it's not the IQ, it's the other stuff. Yeah.
You're not listed to teach a class next semester. Are you doing like research or something?
Yeah, so I'm going on sabbatical for the next 2 semesters. Every 6th or 7th year, professors are entitled to go take a year off and regroup and find new problems to work on, and write more grants or write a book if they want, whatever it is they want to do. So I haven't taken one in 15 or 16 years. In fact, only taken one sabbatical in 26 years. So I'm way behind my sabbatical quota. So I decided to take some time off, relax. What's that? They don't roll. Yeah, it's use it or lose it. So I don't have like 3 or 4 accrued sabbaticals. No, that would be nice, but it doesn't work that way. If you don't take it, you just lose it. It's like vacation weeks during a year. You can't. Well, I guess some companies might let you take accrue vacation time, but no, it doesn't accrue. So I'll come back after a year. I'll still be around occasionally. I just won't be teaching a course the next 2 semesters.
Do you have like something you think you're gonna do?
Try to look for interesting problems to work on. Maybe write some more research grants, get some proposals going. Try to basically reinvent myself as a researcher. Try to, somebody asked earlier, what problem are you going to work on? I'm going to try to figure some out. And it's hard to do while you're teaching. My undergraduate courses, the TAs know, have 200 students in them, and so it's hard to clear your mind and think big and with long periods of time, devoted to insights and research and problem solving when you have to teach a lot and you have a lot going on and students knocking on your door all the time. And so that's one of the reasons of sabbatical is it kind of clears your mind, clears the slate, and gives you time to sit back and reflect and have long periods of time dedicated to whatever it is you want to get done, other than teaching. But I love teaching. I mean, I enjoy it. I don't want to stop it. I really enjoy it. Especially when students benefit from it and appreciate it. As opposed to don't care. So I enjoy helping students and mentoring people and watching them, succeed and flourish and go out and make lots of money. And one of my students, has joined Amazon and eventually made like $450,000 a year. I think it's great. He's now semi-retired. He's in his 30s. That's wonderful. So I enjoy helping people and mentoring and teaching and explaining things in ways that other professors may not be able to do or prefer not to do or don't want to do or can't do. So I want to add value added, basically, in the way I teach. So that's what I try to do in his courses. Is teach it in a way that otherwise will not be taught unless I do it. And I don't want to just drone on and on like the professor from Ferris Bueller Day Off. I don't know if you ever see Mr. Bueller, Mr. Bueller. Anyway, you have to see the movies from the 80s. So yeah, I'll be back. But that's why I'm not teaching next 2 semesters. What else? I'm going to miss the TAs though. They're really good. If you noticed,
Take them all.
Who wants to go to Europe? We'll see. What else? Yeah.
What are some of the fun things to do at Princeton from a computer science book perspective?
Oh, at Princeton? Why do you ask? Are you going to Princeton? Or?
Oh, just question in general. So this section is called Ask Gabe Anything.
Yeah, yeah.
You're not supposed to ask questions.
Oh, well, I mean. All right. So Princeton is. I got my master's at Princeton actually, and it was a bit preppy. It was a bit preppy for my taste as a student. This was back in the 80s. 83 to 85 or something like that. It's Ivy League, and there's a little bit of airs to the people, to a lot of people there. And there's an old joke about Princeton or Harvard, Ivy League in general. It's a new freshman comes to Harvard and is trying to find the library, so he's stopping preppies and asking them. You know what preppies are like? It's like students at these Ivy League schools that are kind of come from affluent families and are kind of out of touch with reality a bit and so on. Anyway, he's asking preppies where the library. We wants to find out, where's the library, and so he asks the preppy, excuse me, could you tell me where the library is at? And the Harvard preppy looks at him and says, "Sir, at Harvard, we don't end our sentences with a preposition." So the guy says, "All right, can you tell me where the library is at, jerk?" Anyway, so I, there was a little bit of that. I came from Los Angeles and other places, and so I went back to UCLA to get my PhD. But Princeton is a great place. Having said that, these are great schools. There's great people there. There's Turing Award winners there, and lots of stuff to do. And I won't ask you why you want to know. All right, what else? Yeah.
If you weren't a professor, what do you think you'd be doing?
If I wasn't a professor, what would I be doing? Assuming I didn't need money, probably a puzzle designer. I think that's pretty good. I mean, I have a large collection of puzzles at my house, over 2,000 puzzles. Like basically every puzzle that was ever on the market, plus many that were never manufactured. They're prototypes made by master craftsmen, for puzzle competitions as prototypes. I love puzzles, and designing good puzzles is hard. If you look at some of the puzzles, they're very clever, very tricky, very esoteric. So that's one option. I guess problem solving in one form or another. Puzzles are a form of problem solving. I like solving problems, and so there's lots of fields where you can solve problems of all kinds. Lots of fields of science. I'll probably be a scientist still. Not sure which one. I have a lot of respect for physics. Physics is hard. It's harder than computer science. In fact, computer science, you don't know how good you have it. Right? I mean, in physics, if you want to find something new, you got to set up experiments. It's expensive. It's labor intensive, and often doesn't pan out. So you have to find a big lab and lots of funding. Computer science, you just run some code. You run it 100 times in one day, and you get some data. And, I mean, it's not trivial, but you have it a lot better than sciences that need physical labs and lots of infrastructure and equipment. So you have it pretty good, actually, whether you realize it or not.
I think computer science is moving towards that.
Maybe, but you can do a whole lot with just your laptop, and that's it. In other fields, it's nowhere near enough. Also, computer science is very immature of a field. There's lots to be discovered, a lot of low-hanging fruit, basically. You can do a lot of different things, and they're publishable. In physics, if you want to publish, I mean, you have to do something new and publishable in chemistry or physics or mathematics. Mathematics has been around for 1,000 years, as a mature field. And you know, it's in mathematics, you have to study for years just to understand what the open problems are, what they even mean. Never mind being able to solve them. Computer science, you can describe an open problem to somebody in 2 minutes, even if they don't know much about computer science. You know, it's a different ballgame. So again, it's a lot easier to do computer science than some other fields, because it hasn't been around for long, and almost anything you do is almost by definition new. You know, it hasn't been tried before, and often it's the case. In math, in physics, and chemistry, it's very hard to find some new problem or problem that hasn't been worked on or haven't been beaten to the ground for decades or even centuries. So just to get to the cutting edge of things in other fields, it's a struggle. But anyway, I'd still be a scientist of one kind or another. I have a lot of respect for science. You know, science doesn't have a lot of pretenses. If it doesn't know something, it admits it very readily. If something works better than what he thought was the case, again, it admits it, it tries to do better. You know, we're not sentimental about theories. Yeah, maybe leave it closed. Let's see if that. Maybe that's a sign that we should wind things down. Any other questions? So science, you know, it's not perfect, but it's one of the best tools we have to understand the universe around us, to get to the bottom of things, to develop, you know, theories that are useful and practical and have value and work. And when we run into stuff that isn't, goes out the window, we try something else. We don't dogmatically cling to things, you know, beyond their, you know, usefulness and expiration date. So I'd be a scientist of some kind or another. Yeah. And as a computer scientist, you are a scientist already. You know, I hope you understand that. You're all scientists by being computer scientists. The computer part of your name is not the relevant one. The scientist part of the computer science attached to your, as a label, that's the important part. Just remember that. You're a scientist first and foremost before you are a computer scientist. So, you know, it's a state of mind, it's a way of thinking, it's a way of exploring, it's the way of doing things. The fact that you're applying it to computers is an afterthought or a secondary, you know, factor. It's not the important factor. You can apply a lot of stuff you learn in computer science to many other fields and still do well and succeed and be useful. So it's not about the computers necessarily. It's about the science part. Dijkstra once said, you know, computer science is about computers as much as, you know, astronomy is about telescopes. You know, the tool is just some artifact, you know, accidental artifact. You know, you can do computer science without computers, right? I hope you realize that. In fact, this whole course was about computer science. We didn't use computers very much at all, actually. What else? Well, we covered a lot of ground, and it's been fun. So if there's no more questions, you know, I'll stop here.